Greetings, my AP Calc BC friends out there. Mr. Record here, and we're going to be taking a look at what is really the tail end of our 10.8 topic, which, for the purposes of my class, ends our study in the convergence and divergence of infinite series, because we like to take care of topic 10.9 and even 10.10 before we finish here with 10.8. So at this point, if you're one of my students at least, you've now gone through the entire gamut of the series tests, and it's ready to start putting them all together and being able to tell what their behavior is. And I can't emphasize enough, there's one aspect of working through a homework set of problems where you pretty much know that every problem is going to be, say, the integral test, or every problem is some kind of a comparison test. But it's a totally different ballgame when they're all mixed together and any single test could possibly apply. And the more that you can practice in an environment like that, the better you're going to be. Trust me. So let's go ahead and take a look at our example 3. We're just going to go through the first 3 problems, parts A, B, and C, and we will just get better with each problem that we do. Here's a little bit of advice, some strategies for testing series. Obviously, it says now that you've studied 10 different tests, that assumes that we include the telescoping series. That assumes that we include the root test and so forth, even the polynomial tests to an extent. But really only 8 of those tests are going to be tested on the AP Calculus exam. Telescoping, root, and even that 11th test of the polynomial test is not going to appear. So now we need to dissect all of these, put them together, and see if we can develop a strategy. So what do I do? What do I suggest? Well, probably the first thing that I would do is look at the series and tell, does it have one of those really special looks to it? Now, I'm not saying that I follow these to a T. Sometimes I can look at a series, just like many of you probably can by now, and clump 1 and 2 together. Is it geometric? Is it P series? Oh, no, not so much. Okay, what about that nth term test for divergence? Could it be used? By the time those are exhausted, and I know it's not telescoping or even alternating, that means I've got to move down into the more trickier tests. And sometimes I clump 3 and 4 together. Sometimes the series has a look where the integral test seems to apply. A lot of times I will try to work with the ratio test first, because it seems, to me at least, to be a little bit more clean. The root test, although not on the BC exam, I look to see, is there a power of n surrounding everything? If I see that, I'm going to go right to the root test. And then typically my last resort is probably one of the 2 comparison tests. And I'll tell you honestly, I'm going to use the limit one before I'm ever going to use the direct comparison test. I have additional handouts that all of my students have now received, and that would be in the form of the convergence flowchart. And in addition, you would have the beautiful Mark Corelli prepared foldable for series convergence. So let's go ahead and take a look at our first few examples here. Determining the convergence and divergence. We're looking at A, which is the summation as n goes from 1 to infinity of n plus 1 over 3n plus 1. Well, remember, we group that first group of tests in a clump. And I know that this is not a P series. I know that this is not a geometric series. So I think, okay, is there a chance that the nth term test might apply? Now, you can probably take that limit in your head very quickly and see, yes, it's going to work. But if this were a free response question, it is very likely that you're going to have to show some justification here, and this would suffice perfectly. Obviously, if it's multiple choice, you can do all of this in your head. So yes, we know that we have a limit of 1/3 here, which is not equal to 0. So we can say that this series diverges. And I would like to go ahead and identify the test by which works. And I'll just say the nth term test. I normally call this test the nth term test for divergence, but I will spare you the agony of writing that for divergence phrase out, and we can just stop right there. Taking a look at B. In part B, we look very quickly. We recognize hopefully that this is a geometric series. We recognize the fact that the absolute value of r in this case is pi over 6. Pi being 3.14 means that this fraction is indeed less than 1, and that's all we need to know to tell that this is a convergent geometric series. Now, as we wrap this example up, is it possible that either of these two examples could have been answered using a different test? Yes, it is very possible that that may be the case, especially in the case of part A. We could have thought about applying perhaps maybe some kind of a comparison test. So these tests aren't sort of isolated or pigeonholed into only working one time and one time only for a certain series, or a series working only one time for a certain test. So what I would encourage you to do is find the test that you think is easiest and most productive for you. Let's go ahead and take a look at our last example. This one is a very interesting one. You've got the summation of n times e to the negative n squared power. Now, it's very likely that some of you who are very astute, especially with your integration techniques, notice this thing integrates very nicely. By golly, I think if I were to take my u as this exponent, the derivative of that would be negative 2 times n, and that would match up with this n very nicely, and therefore, therefore we would be able to use the integral test. Now that's as long as the integral test would apply. That's something that you've got to consider. I also know that we could probably investigate some other tests that might be a little easier than the integral test. So I wanted to use this opportunity to take a moment to look at a problem that you normally would think integral test for, but try it with the ratio test. So the ratio test says we're going to take the limit as n approaches 0 of the absolute value of the nth plus 1 expression, which, as I write this nth plus 1 expression, I'm going to go ahead and drop this e to the negative exponent down to the denominator. And I'm going to write it like that, let's say. And then all of this would be over the original expression, again, with that e to the negative n squared dropped below. Okay, well now where does this take us? Well, we're going to go ahead and analyze the usefulness of our absolute values, or lack thereof, and realize that we can do away with them. And at the same time, I'm going to go ahead and multiply by the reciprocal. So when all is said and done, this n plus 1 up in the numerator is going to be joined with an e to the n squared, and the denominator would consist of an e to the n plus 1 squared that I'll just write here in the second spot so that I can put my n there in the first spot. And so now I'm looking for a way to simplify this so that I can find the particular limit here. Well, we do notice that the n plus 1 over the n, by the time we separate that from the rest of this, we simply have a limit of 1. This part here is not going to really affect much of what's happening with the part that comes afterwards. So I'm going to go ahead and do away with that. I don't want to even insinuate that the n plus 1 over n cancels, but we just end up having a limit of 1. And just to make sure that I communicate that effectively, I'm just going to split it apart like that, and then I'll move over to the limit of the other portion. Now, because we are dividing like bases of e, we can subtract these exponents. Now, as I do that, I'm going to work here off to the side, And I'm going to expand that n plus 1 quantity squared here for us, so that when I do subtract those exponents, it's clear to me that I would get negative 2n minus 1. All right. Well, remember we said that this limit is going to be, of course, 1. And then the limit over here, if we think about one more little quick rewrite, notice how this negative quantity, or negative, I should say, 2n minus 1, could be negative quantity 2n plus 1. I could bring that whole e down to the bottom with that power that's now positive. And I think it's pretty clear to see that this limit is going to produce a very large denominator that's going to be 0 overall. 1 over really, really big is going to be 0. So 1 times 0, of course, is 0. And remember, the conclusion of the ratio test only asks that our resulting limit be less than 1. And because of that, we can say that this particular series converges by the ratio test. Probably was one of our more complex ratio test problems that we've done. But I would say that by and large, this was quicker than if we had used the integral test. Because remember, with the integral test, you would have been obligated to show that it even applied by mentioning the 3 criteria, that this expression was going to be positive, continuous, and decreasing over a certain interval to infinity. Anyway, I hope this helps with the first 3 in our example 3. We're going to take a look at parts D, E, and F in the next video to wrap up some more review with the convergence test. Thanks for joining. We'll see you next time.